Hello again, everyone. So we are going to be doing our lecture on logarithms in this video. Um, so last video we talked about exponentials, which are these lovely functions where you take some base and some real number base and you raise it to a power over time, right? They all tend to have this kind of appearance to them. These were some functions from an example last time. They have this infinite long tail going off to the left, usually with a horizontal asymptote at y equals 0, though if there's some sort of transformation that might change. For example, if I do like plus 7,000 to this one, I was not graphing that. You'll see it has a horizontal asymptote at 7,000 now. But let me graph just a basic exponential for you now, because let's say I just have the exponential 10 to the x power. Resetting my zoom here a little bit. You can see that just make this zoom square. There we go. Zooming back in. So, this is what the function 10 to the x looks like. It starts off, again, it has this tail that goes down towards 0, but never quite reaches it, even though Desmos eventually gives up on telling you and just pretends it's 0. If you zoom in, you'll see it's not quite. It has this point at 0, 1, because 10 to the 0 power equals 1, right? 10 to the x. And even already when x equals 1, we're already zooming right up to 10, right? Because 10 to the 1 equals 10. At x equals 2, we already zoom all the way up to 100, so we're not going to hit x equaling 2 until we get here at 100. And obviously, we'll have the point 3, 1,000, and 4, 10,000, and 5, 100,000 on this graph. So it zooms up really quickly. Now, being able to graph something like this on a computer implies some interesting things, right? Because while it's easy for us to calculate points like 1, 10, 2, 100, 3, 1,000, how does the computer know what to do, for example, when I plug in 0.5? It seems to have an answer, right? It says that when I plug in 0.5, that I get 3.162. Oh, I guess that means 10 to the 1 to the 0.5 power equals 3.162. That's actually the same as saying the square root of 10 is 3.162, right? Approximately. That 3.162 is almost definitely rounded. But it's interesting because I can't just look at 0.5 and whole numbers. I can look at any x value and get a y value out, right? This implies that somewhere, somehow, my computer is solving a problem that looks like this. If I want to look at, for example, what do I do when, let me do an even nicer thing. I'm going to graph the number 7 here. So this is just going to be the line at x equals 7, or sorry, y equals 7. Doesn't want. All right, let me see. Y equals 7. Now, if I look at where that function meets my function, I get this little piece of information, that 10 to the 0.845 must equal 7, right? So somehow my computer is able to solve a problem of this form. It's able to say, okay, if 10 to the x equals 7, what is x? And the computer seems to be able to get an answer, right? The computer just told us x is about 835? 845. And so that begs the question, how the heck is the computer doing this? Well, for a long time, the answer was simply that you would make these calculations. There were ways to make estimates, right? So, for example, I know that 10 to the 1 equals 10. So the number that I raise myself to get 7 must be less than 1, right? I know 10 to the 0 equals 1, so the number I raise 10 to get 7 must be more than 0. All right, that's not great, but it's a start. And what about, okay, I know that, let's say, words. But there's tricks like that you can use to get these approximate answers. And for a long time, that was what we had, right? We would use these tricks and we get these approximations. And we could be clever to find more accurate approximations and things like that. But effectively, what we had were these big books full of calculations people had already done, answering questions like this. And one word for a book like that would be a logarithm. But in general, what we have here is basically, mathematicians defined a formula. We said, okay, I'm not going to even say solve, I'm going to say to represent questions like this, as a function, we defined f of x equals the log base b of x to be the solution to b to the f of x equals x. So it's going to take a second to understand this here. In fact, I'm actually going to slightly modify this the way I've written this. I'm going to say, because we're going to talk about f of x equals log base b to the x, but I think it's a little bit more helpful to think. We defined it to be, okay, x equals log base b of a. Here this base is a subscript, like the b should be smaller and written underneath the log. But the a is in parentheses and the same size as the log and on the same level. It's like when you see like H2O, the 2 here is a subscript, the b here is written as a subscript. To be the solution to b to the x equals a. So what we're saying here is we're defining a function called a logarithm, which we abbreviate as log, L-O-G. And the log has a base, which represents some number that's being raised to a power, and it has an argument that you plug into it, just like sine and cosine or other functions have arguments that you plug in parentheses. So this is not multiplication. This parentheses a is function notation. And we define the logarithm base b of a to be the power you would raise b to get a. So I'm going to write that down because that's important. So log base b of a is the power you raise b to in order to get a. For example, log base 10, or actually that might be, sorry, I took a look at the first few problems on there. Yeah, no, I like mine first. I'm going to give my example first. Log base 10 of 1000 is the number, the power that I would raise 10 to if I wanted to get 1000, right? Again, log base b of a is the power you raise b to in order to get a. So I would read this as the power I raise 10 to in order to get 1,000? Think for a second. What power do I raise 10 to get 1,000? I feel like Dora the Explorer. That's right. It's 3. Because 10 to the third power equals 1,000, right? 10 times 10 times 10. And so based on that, you could also answer a question like, what is the log base 5 of 25? What power do I raise 5 to get 25? Say it with me. It's 2. That's right. 5 squared is 25, so we would define the log base 5 of 25 to be 2. Now, this doesn't fully explain all the clever tricks we could use to get those in-between values, like log base 5 of 12 or something weird like that. But this does mean that just with this, because the exponential function is well defined, the logarithm, which is its inverse function, is also well defined. So let me actually give us a new layer here. So here are the notes they actually wanted me to give you. F of x equals log base b of x is the inverse of g of x equals b to the x. What they mean by that is this. An inverse function reverses x and y, right? It switches inputs with outputs, and if you compose them together, they cancel, right? And so if I were to go here, I have my beautiful 10 to the x here, which is an exponential. If I now want to graph log base 10 of x, notice that these graphs have this beautiful symmetry to them. Specifically, they have a symmetry over the line y equals x. They're mirror images of the line y equals x. Meaning, for example, if my first function, 10 to the x, has the point 0, 1, then its inverse must have the point 1, 0, where those numbers are switched. And so on. Like, if we have the point here at, I was saying earlier, we have the point at 1/2. I'll do a nicer point. Well, we have the point 110 on this function here. That means we have the point 10, 1 on its inverse. And so on. Every single point on the green function, if you switch its x and y value, gives you a point on the black function, and vice versa. Again, the green function here being the exponential with a base of 10, and the black function being the logarithm with a base of 10. Now, if I were to graph, for example, 2 to the x, its inverse function would be called log base 2 of x. And you can see that this blue function and this green function, if I hide the other ones there, this blue function and this green function also have that same symmetry over the line y equals x. And thus they also have that same property where for every point on the blue function, if you switch x and y, you should get that same point should be on the green function. So that's what it means for two functions to be inverses. The other thing it means algebraically is that if you compose these functions together, you always just get x. So like 2 to the power of log base 2 of x equals x, which we'll go over in a minute. So this is really important. We've defined that log base b of x is the inverse function of g of x, or of b to the x, right? And as a result, it gets a bunch of properties for free by being an inverse function, right? The domain of an inverse function is the range of the original. So we would say that the domain of log base b of x is from 0 to infinity. The range is from negative infinity to infinity, just like the domain of our exponentials earlier. We always have an x-intercept at 1, 0. And I'm going to say here, Oh, and we always have a vertical asymptote. There was a horizontal asymptote on the exponential, so we always have a vertical asymptote at the value x equals 0. This makes sense because if you ask the question, what power can I raise 10 to get 0? There isn't an answer. There's no power you can raise 10 to that makes it 0. If you raise 10 to the 0, remember you get 1, not 0. And so, because there's no answer to the question, what power do I raise 10 to or 2 to get 0, you can see this green function here, our logarithm, has a vertical asymptote at x equals 0, and at 0, it's undefined. And notice also, there's no power I can raise positive 2 to get a negative number, so that's why our domain doesn't include any negatives. Because the power you raise 2 to get negative 2 doesn't exist. There isn't one. Or at least it's not a real number. So we have a vertical asymptote at x equals 0. Our domain starts at 0 and goes to infinity. And we're not defined over the negative numbers for logarithms. Now, looking at our worksheet, they ask us to write the following in exponential form. Log base 5 of the square root of 5 is 1/2. So when they say to switch to exponential form, what they're just saying is we defined logarithms based on exponentials, right? Log base b of a equals x is the same as b to the x equals a. So just convert this back into that b to the x equals a form. Remember, this number we call the base. This is called the argument, which is the number that's being plugged in. Sometimes you'll see it written with or without parentheses, but it's always the same size as the logarithm here. It's not a subscript. And then you could think of this as either the answer, or as I like to think about it, the exponent, because the answer to a logarithm is a question, and the question is, what exponent do I raise my base to get my argument? So its answer, its value, is always an exponent. This is the same thing as saying that the base, 5, raised to the exponent 1/2 equals the argument square root 5. So this would be that phrase rewritten in exponential form. And so, but by the fact that this answer that we just gave is a true statement, 5 to the 1/2 is defined to be the same as the square root of 5, that must mean that the log base 5 of square root of 5 really is 1/2. So the original statement is also true. Again, we can do the same thing over here. So this is saying, again, we have the logarithm with the base of b and an argument of a equals x is the same thing as saying that b to the x power equals a. So here, our base is 3, so that's the thing being raised to the power. The power is -3 because the answer to a logarithm is an exponent, and the argument is the number that you would get as a result. So 3 to the -3 equals 127. So those would be our two answers for 1. Again, take some time with this, but the literal definition of logarithms is just that if you have an expression that looks like this, then it's equivalent to this expression. So if some number to a power is equal to some other number, then the log base of the number being raised to the power of the result is the exponent. Like, that's how we define the logarithm function, or I guess the class of logarithm functions, because you can think of each logarithm with a different base is like a slightly different function from each other. So like log base 5 is a different function from log base 6, is a different function from log base 10. Now, here they want us to do the opposite. They've given us an exponential statement, and they want us to convert it into a logarithmic statement. So we can still use this same rule from up here. So if 6 cubed equals 216, that means the power I raise 6 to get 216 is 3. Again, I didn't write 6 to the 216 power there on the left. That's a subscript 6, which is telling me the base of my logarithm. And then in the parentheses there is the number 216, because that's my argument. So again, this reads, the power I raise 6 to get 216 is 3. That's how I would read that in words. Again, here they're saying 5 to the negative 1 is 1/5. So if I want to rewrite that as a logarithm, I say the power I raise my base 5 to in order to get 1/5 is negative 1. So it's really just a difference in like sentence structure, right? The only difference between an exponential and a logarithmic statement is the sentence structure. A logarithm says a base to a power equals a number. And a logarithm says the power I raise a base to get a number is this power. Now they want us to graph these logarithmic functions, find the domain and vertical asymptotes. These are just some transformations of basic logarithmic functions. So this is like log base 2 of x, but then plus 2. As you're getting started, if you're more comfortable with exponentials, one thing you could do here is think about what's the exponential that this is the inverse of. Like log base 2 of x is the inverse of 2 to the x, right? 2 to the x looks like this, as we went over in a recent lesson. And to get its inverse function, you can just reflect it over the line y equals x, and so that'll give you something that looks like this. But remember, we're not just actually graphing this. We want this shifted to the left 2 units, because that's what that x plus 2 on the inside there is. That's a horizontal transformation, or horizontal translation, I should say. So our actual function is going to look like, this point, remember, is usually at 0, 1. That's what I said over here. We have an x-intercept at 0, 1. Oh, sorry, 1, 0. I keep saying that backwards. An x-intercept at 1, 0. 0, 1 would be a y-intercept. And you can see that here. We have this point here at 1, 0, because what power do I raise 2 to get 1? I raise it to the 0 power. And so, going back here, this point at 1, 0 is going to be shifted 2 units to the left to negative 1, 0. The horizontal asymptote at y equals 0 is also going to shift 2 units to the left. So this is now a horizontal asymptote at negative 2. And so my function will look something like, you can ignore that point on the right there, like this. If you like, they don't ask you to, but you could find the y-intercept here by just plugging in x equals 0 to this function. You'd get log base 2 of 2, which is 1, so this point here, it must be 0, 1. And they asked you to find the domain and the vertical asymptotes. So the domain here, again, our domain is normally 0 to infinity, but we've shifted to the left 2 units, and so our domain starts a little earlier. So our domain is going to start at that vertical asymptote at negative 2 and go forever. And our range is going to be what it always is, which is negative infinity to infinity. Now over here they have log base 3 of x minus 5 plus 2. Again, this is just 2 transformations of a basic logarithm. The regular log base 3 would have this point at 1, 0 and would look like this, right? This one is just going to move to the right 5 units and up 2 units. So this point at 1, 0, you can add 5 to the x value and 2 to the y value, and you'll get, on our actual graph, the point 6, 2. Our horizontal shift was 5 units to the right, so our vertical asymptote at x equals 0 is going to also move 5 units to the right. So this is at x equals 5. And so we're going to look something like this, where we approach that vertical asymptote, and where we go up and to the right forever. Again, there's no horizontal asymptote on this function, so there is no like maximum value that it reaches. As x keeps increasing, the log base 3 of x will keep increasing as well. So again, this was our original. This was like a reference that we used. This was log base 3 of x. But we want log base 3 of x minus 5 plus 2, which is this one. Our domain here is, again, we've shifted to the right 5 units, so we're now starting at 5, but we're still going to infinity. Our range is still all real numbers, because nothing that happened here could affect the range, being all real numbers. Zoom out and give you all that. Now, again, we're going to talk about a few rules about logarithms here. These mostly come from either, you can think about this from either the definition I gave you, which is that a logarithm is a question. It asks the question, what power do I raise my base to get my argument? What power do I raise my base to get the argument in parentheses? I also need to give you a few quick definitions here because they are going to use, so there's some standard notation they're going to use here. So, if you see log, but with no base, there's no number written there, that always means log base 10. This of x thing just means of anything, right? So log means log base 10 if you don't see a base. ln, this is not an I, but an L, ln of x means log, and again, this is not iog, this is log, L-O-G, for logarithm. Logarithm, by the way, comes from the ancient Greek, meaning logos, which means like reasoning or ratio, and rhythmos, which means number. It was not named by the ancient Greeks, it was named by Europeans who loved the ancient Greeks. It's a thing that Europeans did for a few centuries. So loosely it means ratio number, which is a little unhelpful, but ln of x means log base e of x. Here, e is the natural number that we got before. It's approximately 2.71. It's the number that showed up in our last video when we talked about the limit as n approached infinity of the compound interest formula. E suddenly showed up. It turns out E is super important, and ln, as a result, is also super important when talking about exponentials. Like most things that look exponential in the real world turn out to have a base of E. Or at least many things do, or their bases are related to E in some way. And so ln is a really commonly used, ln is short for like log natural or something. It stands for it's called the natural logarithm. So this is sometimes called this here is sometimes called, I keep meaning to change my color but not changing the brightness. My first time using Photoshop for this. This is sometimes called the standard logarithm, Logarithm, and this is sometimes called the natural logarithm, because it turns out that ln is it pops up everywhere. I'm just gonna, like, if you're doing actual like hard mathematics or like abstract mathematics, the natural logarithm pops up a whole lot more than log base 10 does. We just like log base 10 because our number system is in base 10, and so logarithms in base 10 actually make a lot of sense with how our number system works. Anyway, so those are just some standard names that we give to functions. They're like nicknames, right? Log of x is just a nickname for log base 10, whereas ln is just a nickname for log base e. Now, for some actual rules, sometimes called, or I'll call these the properties of logarithms. We'll do like a nice golden color here, golden brown. So here are a few properties of logarithms, and all of these come from a place of if you look at the definition that I gave earlier of a logarithm, that it's a question that asks what power do I raise my base to get my argument, or they come from being an inverse function to exponentials. So here's what I mean. Here's a nice simple one. A log base b of b is 1. Why is that? Well, let's think about what the equivalent exponential expression to this is. The base of b raised to the 1 power equals b. Oh, that's kind of obvious, right? So if a number is raised to the power of 1, it equals itself, which means that the power you raise the base to get itself must be 1. The log base 7 of 7 is 1 because the power you raise 7 to equal 7 is 1. So log base b of b equals 1. Here's another nice one. Log base b of b to the x, by the way, this could just be written like that, is x. This comes from, well, first of all, it comes from the very obvious exponential equivalent is just b to the x equals b to the x, right? The power I raise b to get b to the x is x. But the other way you think about it is this comes from because log base b of x is the inverse of b to the x. And we have a rule about inverse functions, which is that if you stick one inside of another, they cancel out, right? And so if you think of this, for example, as f inverse of x, and you think of this as f of x, then this is f inverse of f of x. And if you remember from our lesson on inverse functions, that always equals x. That's one of the definitions of an inverse function, is that if you compose it with the original, you get x. Now, that definition works in both ways, right? F of f inverse of x is also x, and so we get this second lovely fact. B to the power of log base b of x is also equal to x, because this is just the same thing as saying, that this over here is just f of f inverse of x, which we know, again, from our inverse functions lesson, is just x. And again, I'll zoom out here to give you these properties. I'll make sure to show them on screen for at the end. Now let's see. Are there any other good ones that I should give you? Oh, there's some ones that use zeros and ones. So, there's a corollary of this one, log base b of b equals 1. This means ln e equals 1 as well, because ln is just log base e of e. So that's just this rule again, right? Where a log base b of b equals 1. In this case, we're just plugging in e, the number, for b, the variable, right? So, of course, the power you raise e to get e is 1. So ln e equals 1. Then we also have, for example, similarly, log 10 equals 1 for the same reason. Log base 10 of 10 equals 1. Now, the last couple here are log base b of 1. The power I raise any number to get 1 is always 0. Any logarithm, that's natural log, that's the standard log, that's log base pi, log base 700, anything where if it's of 1, log base pi of 1 is 0, because the power I raise pi to get 1 is 0, right? Again, this goes back, if you switch it into exponential form, you get the statement b to the 0 equals 1, which is a true statement. And so switching that statement into logarithmic form is what gives us that fact that log base b of 1 equals 0. I'll mention here log base b of 0 is undefined. We've said that. Log base b of any negative number is undefined. I'm not going to keep that up there. This, of course, means, because log base b of 1 equals 0, this means that log 1 equals 0 and ln 1 equals 0, right? Those are just cases of this, here where b is 10 and here where b is e. So these are just like special cases of log base b to the 1 equals 0. The real important ones here, which I'll highlight in gold. Log base b of 1 equals 0 is important. Log base b of b is 1 is sort of important, technically speaking. It's just a special case of this one, which is the really important one. Log base b of b to the x equals x. And then b to the log base b of x equals x is also really important. So those four are the ones I would think about. This other stuff here, like ln e equals 1 and log 10 is 1 and log 1 equals 0 and ln 1 is 0, those come from this one and this one if you just plug in the bases of those logarithms for b. I would take a screenshot of this. I would make sure pause your video, make sure you understand these things, and honestly, pause your video and try and complete the next problem on your own. I'm going to jump in and do it, but I'm expecting that you're going to take a moment now to pause your video and work on these on your own. All right. Glad you're back. So this is, remember, log base 100. Log base what, right? Log, this is the same as saying log base 10, right? Because we said log just means log base 10. So what power do I raise 10 to get 100 to the 8th power? Well, one way to think about this is 100 is just 10 squared, right? So this is like log base 10 of 10 squared to the 8th, which is the same as saying log base 10 of 10 to the 16th. And we have a definition that says log base b of b to the x equals x, so this must be 16. The other way to think about that is, what power do I, like, you could literally just calculate what 100 to the 8th is, which is a 1 with 16 zeros at the end, and then you ask yourself, well, what power do I raise 10 to get a 1 with 16 zeros at the end? And if you know anything about powers of 10, the answer to that is you raise it to the 16th power. B here, e to the ln 3. Again, this is e to the log base e of 3. If you look back here at this, b to the log base b of x equals x has the side effect that e to the ln x equals x, right? And also that ln, and this one over here has the side effect that ln of e to the x equals x. Those are just, again, you just plugged in e for the base, right? The base is just any number, and e is a number. So because we have e to the ln of 3, that must exactly be equal to 3. The other way to think about this is, this literally says the power, or sorry, it says e is raised to the power you raise e2 to get 3. Right? ln3, log base e of 3, is literally the power I would raise e2 to make it equal 3. And then you raised e to it. So it's e raised to the power that when you raise e to it makes it equal 3. So obviously it has to equal 3. That's the whole definition. C, this is the power I raise b2 to get b to the 15th. So again, you could think about this with this question. The power I raise b2, the power I raise b2 to get b to the 15th. Well, that's very obviously 15. But again, if you look back at our rules, this is log base b of b to the x equals x, right? Log base b of b to the x equals x. Here, x was just the number 15. So if you have a log base b of b to a power, the answer will always be that power, because you'll always be able to interpret it like this. The power I raise b to get b to the 15th. Well, of course that's 15. Here, we could think of this as the power I raise e to get 1 over e to the 8th. Now keep in mind, 1 over e to the 8th is the same as e to the negative 8th, and so the answer here is negative 8. Here, that same rule, 3 is being raised to the log base 3 of 4x, so that's 4x. Here, e is being raised to the ln of log base 3 of b. This is really confusing when you look at it, but e to the ln anything is just the thing. because these are inverse functions. E to the power and ln of something are inverse functions. So this comes out to just log base 3 of b. Because again, our rule here says e to the ln x equals x, so e to the ln log base 3 of b equals log base 3 of b. Again, these can be confusing at first. If you start to internalize those rules, and I highly recommend you do it by either thinking about what the equivalent exponential version is, like translate the rule into an exponential statement and see if that makes sense. Or use this definition that I've been doing, the power I raise my base to get my argument. That will almost always work out. Because, like, again, here we're saying I'm raising e to the power I would raise e to get log base 3 of b. So I should get log base 3 of b. Last thing on this page are going to be the rules of logarithms. So there's a very nice thing. The logarithms have these really nice properties. And one of those nice properties is called the product rule. The product rule says log base b of, I'll just say I'll say n and m. Log base b of n plus log base b of m equals log base b of the product of n and m, n times m. Sorry, get rid of that there. And this works in both directions, right? So if I have, for example, log base 10 of 2 times 3, I can calculate separately what log base 10 of 2 and log base 10 of 3 are and add them together. We then have, I'll do a different color, the quotient rule, which is the exact thing but with division and subtraction. Log base b of n minus log base b of m equals log base b of n over m. Notice the only thing that b is doing in this is that it has to be the same for the two logarithms that are being added or subtracted in order for the rule to apply, right? So if you're using the rule from the right side to the left side, like breaking up or expanding that logarithm, like if you start with something that looks like this and you want to make it bigger, and so you're going this way, then you don't really have to worry about it. Just keep that base the same for those things. But if you have two logarithms added together, make sure they have the same base if you're going to try and use this rule. Otherwise, you can't. So this is the quotient rule, which means the same thing. Again, notice that the one that's in front of the minus is the one that's on top in the division. The one that's behind the minus is the one that's on bottom in the division. That is important. And then finally, we have the power rule. I'll do it in pink here. Which is a really neat one, which says that any number a times log base b of n is the same as log base b of n to the a power. So again, here, this is the argument. We're not usually allowed to mess with the argument from the outside, but these three rules are rules about how you can, right? So the quotient rule says that if you have two different logarithms subtracted, you can make them into a logarithm of those two arguments divided by each other. The product rule says if you have added two logarithms with the same base, then you can multiply their arguments to get the new argument and combine them that way. The power rule says a number being multiplied on the outside of a logarithm is the same as the entire inside of the logarithm being raised to that power. And so, again, you can use this in both directions, right? This means that, for example, log base 10 of 10 squared is equal to 2 times the log base 10 of 10, right? That's what this here, a is just 2, which is nice because I happen to know log base 10 of 10 is 1, and so log base 10 of 10 squared is 2. Hey, that's our rule from before, log base b of b to the x of x. So again, I'll zoom out here and I'll show you these three rules: the product rule, the quotient rule, and the power rule. Together, these are known, even though they're usually called rules, they're known as the laws of logarithms, sometimes abbreviated as the laws of logs. This last thing was just an example, it wasn't the law. So the product rule says adding on the outside is the same as multiplying the arguments. The quotient rule says subtracting on the outside is the same as dividing the arguments. And the power rule says that multiplying on the outside is the same as raising the argument to a power. And if you want to convince yourself why each of these would possibly be true, feel free to. I don't have the time to do that today. But there is a reason, right? It does actually make sense. For example, this here, if you test it out with a few calculations, you'll start to get a sense for why the power rule makes sense and things like that. But going back to try applying them, when they say expand the following as much as possible using the rules of logarithms, sometimes, yeah, again, the laws of logs are the rules of logs. Expand just means write this as the longest possible, like the most different logarithms that you can. So for example here, I can write this as log base 3 of 3 plus log base 3 of x plus log base 3 of y. Now, technically speaking, if I was being nitpicky, this would become a 1. I would accept either of these answers, though, unless they specify that you should keep everything in log form or that you should simplify anything that could simplify. So this is what they mean by expanding. Here I just used the product rule, right? I saw that these three things were being multiplied on the inside, and I'm like, well, that's the same as adding them as separate logarithms, right? And you can see, if you use the laws of logs to combine these, you're going to get what we started with here. So that's when they ask you to expand a logarithm, that's all they're asking you to do. Here, we'll do the same thing. We're going to use the quotient rule and the product rule here, because we're going to use the quotient rule to differentiate the top from the bottom. So you can think about this in two steps, right? The first step would be that this is log base 5 of 25a minus log base 5 of b. Again, you can put parentheses around here or not. And then this is going to expand further, right? So that with the product rule, we can say that that's log base 5 of 25 plus log base 5 of a, and then we still have minus log base 5 of b here. And again, this does evaluate out to 2, so depending on the problem, you might want to put a 2 there instead of a log base 5 of 25, because that's the power you raise 5 to get 25. All right, we're going to take a quick look at that next page. Hopefully the rest of this is mostly going to be stuff that you should be able to do with the information I've already given you. So yeah, like here, this is just more experiments with that same process, but here the only thing is they want you to also use the power rule. So like this becomes ln e cubed plus ln x to the fourth plus ln y to the negative fifth, but you can use the power rule to get rid of all these exponents. That becomes 3 ln e plus 4 ln x minus 5 ln y. And so, there we go. Over here, same idea. Log of x to the fifth plus log of y cubed minus log of 10 minus log of z to the fifth. Notice you can think of this, you first did minus log of 10z to the fifth, and then you split this up with the product rule, but then this minus distributes. So this all ends up being 5 log x plus 3 log y minus log 10, which is just 1, minus 5 log z. Again, this number could be rewritten as a 1, because that's what power do I raise 10 to get 10? The answer is 1. This is just the reverse of that, so we're rewriting as a single logarithm. So this becomes log of x cubed minus log of, this is important, x plus 5 to the fifth power is what this logarithm is of. Alright? And then this is plus log of the square root of 3x plus 4, because a 1/2 power is the same as a square root. So when we finally combine this, and again, be careful about the minuses and pluses here, this is the only one being divided, so the other one is going to get multiplied because it's being added. So we get log of x cubed times the square root of 3x plus 4 all over x plus 5 to the 5th. This is all in one big logarithm, so that would be our final answer there. Here, we're going to have ln a to the 8th plus ln 2b plus 1. Keep that in parentheses so you know that it's all one ln, it's not a plus 1 outside, minus ln of c to the 1/3. You could also call that cube root of c if you prefer. And that combines into ln of a to the 8th times 2b plus 1 all over c to the 1/3. You could multiply this out to be a to the 8th, like 2a 8th b to the 1st plus a to the 8th, but you don't need to. And again, this whole thing is inside this natural logarithm. Change log base 3 of 5 to a quotient of natural logarithms using the change of base formula. So this is a new formula that I haven't given you yet. This is maybe the last fact I need to give you today. The change of base formula. It's a lovely little thing, and it's good because your calculator, you may have noticed by this point, only has a button for log base 10 and maybe ln. Right? It just has log and ln. It doesn't have a way to put in the base on most calculators unless you have a nice fancy scientific calculator. So we need something called the change of base formula in order to even use our calculators to calculate logarithms. And this formula seems wild. It seemed wild to me when I first saw it, but it does work. And I encourage you to spend some time at home doing calculations with it and trying to figure out why the heck it should work. But it tells you this. If you want to calculate log base b of a, that's the same, or sorry, I should say, yeah, that's whatever. Log base b of a, that is the same as log base n of a over log base n of b, where n is any other base. So for example, if I want to do log base 7 of 49, which we know should be 2, I can rewrite that as log base 8, or whatever, of 49 over log base 8 of 7. I didn't pick 8 for any particular reason. I just said, like, basically this 8 could be replaced with anything. And it's always true, right? So if this 8 was replaced with an 81, for example, that would also work, right? If this 8 was replaced with an E or a pi or a 7 or a 12, any of this is all fine. So like this is the same thing as just log 49 over log 7. This is what you would normally do in a calculator to calculate log base 7 of 49. You would do log 49 divided by log 7. You could also do ln 49 divided by ln 7. All of this means the same thing as log base 7 of 49, which I think is wild, because why the heck would that work? I have seen a proof of it. It is true, but I encourage you to look into it yourself, because if I just tell you it's true, that's hard to remember, but actually learning why it's true, you will understand it and you will not forget this really important formula. If you don't know this formula, there will eventually be a point where you're in big trouble on the test. Especially if you want to use your calculators to evaluate logarithms, you need this formula. Again, this just says n, it can be any other base you want. If you want to calculate log base b of a, you just do log base something of a over log base that same thing of b. Alright, so going back here, that means our, this expression, they said of natural logarithms, so they're asking us to use ln. So log base 3 of 5 equals ln sorry. You can write ln like this, but I have a habit of writing it like that, so you can really see it's an L. ln of 5 over ln of 3. And again, you don't need the parentheses, but it's nice to have them. Same thing here. They wanted common logarithm. Sorry, when I said standard logarithm before, I meant common. So this is log base 10, or log. So the common logarithm, so log base 7 of 10 must equal log 10 divided by log 7. So the power I raised 7 to get 10 is the power I raised 10 to get 10 divided by the power I raised 10 to get 7. And then the rest of these are solving equations, which you can do by using the fact that logarithms and exponentials are inverse functions of each other. So, for example, here, I wouldn't do anything at this stage. I'm going to get the ln on its own first. Subtract 6 from both sides. So I get ln x equals 4, right? And again, of course, they just say solve the equation, so we're assuming we're solving for the only variable there, that's x. So how the heck do you break an ln out of, or how do you break your variable out of an ln? To break out a variable from a logarithm, use an exponent, or use an exponential. What I mean here is, there is something that you may not have seen us do in the past, but that we are allowed to do. We are going to raise e to both sides. What I mean is, we're going to go e to the ln x equals e to the 4th. Now, because I've applied the same function to both sides, the usual rule of algebra applies here, which says that I have not changed the truth value of our statement, right? And so, now I can use some properties, like e to the ln x equals x is a property that we have, right? So this just cancels out to x equals e to the 4th. I'll get rid of that box because it's covering up that last problem. But that's our answer. X equals e to the 4th. So 6 plus ln of e to the 4th equals 10. That makes sense because ln e to the 4th is 4, so 6 plus 4 equals 10. Down here, 2 ln of x plus 1 equals 10. Again, I'm going to divide both sides by this 2 first, because I want to wait until we have like ln of something equals something. So we have ln of x plus 1 equals 10. Again, I'm going to raise e to the power of both sides, which sometimes people write just like that. So e to the ln of x plus 1 equals e to the 10th. This cancels, and we get x plus 1 equals e to the 10th. The other way of thinking of this, by the way, if you don't want to think about raising e to both sides, you can think instead about convert to exponential form. Because before, without these e's here, what we had was ln of x plus 1 equals 10. The exponential form of that statement is that e to the power of 10 equals x plus 1, right? The base to the power equals the argument. And so it's the equivalent, raising e to both sides is the same thing as converting between logarithm and exponential form. And again, we're only using e to raise to both sides because the problem includes ln. If the problem was like log base 5, we would raise 5 to both sides to cancel it out. So if you're confused by that, you can just think about converting to exponential form, and that will always work. So here we've converted to exponential. We're in e to the 10th equals x plus 1, so this becomes very easy. X must equal e to the 10th minus 1. E is a number. E to the 10th minus 1 does not simplify. Please don't try to simplify this. E, it's like if I said pi times pi minus 4. You wouldn't try and mess with that because pi times pi is a complicated number that you just don't want to, like, there's not a good way to do it. Just like if e was a variable, we're going to leave this be. X equals e to the 10th minus 1 is our final answer. All right. So here, this is really nice. If you've got ln of one thing equals ln of another, This is a property that happens because ln is something called a one-to-one function, but you don't really need to know that. The important thing here is that we can raise e to the power of both sides to cancel out both ln's at once. Again, this only works because the whole thing on the left and the whole thing on the right are inside the ln function. If there was like a +1 here, we'd kind of be screwed. And we'd have to do something a little bit clever, like subtract ln of 2x plus 3 from both sides and then use the quotient rule. But because we don't have that, we can just say e to the this equals e to the that. E to the ln of x squared is just x squared by one of the properties we learned earlier, right? E to the ln x is x. And e to the ln 2x plus 3 is just 2x plus 3. So we get this nice thing, which becomes a quadratic, x squared minus 2x plus, minus 3 equals 0. This factors nicely into x minus 3 times x plus 1 equals 0. The zero product principle says that we can set each of those equal to 0 and solve. We get x equals 3 and x equals -1, both of which will work if you plug them back in here. So ln of -1 squared, that's ln of 1 is 0. Should equal ln of 2 times -1 plus 3, that's again ln of 1 is 0, or ln of 9 equals ln of 2 times 3, 6, plus 3 is also 9. So yep, both of those answers work, 3 and 1, -1. Finally, here, what I would do before trying to solve any of this, because this is really ugly, is I would use our rules of logarithms. So instead of trying to mess with 3 logarithms at once, because you can't just say like 10 to the this and 10 to the this and 10 to the this, it doesn't work. Because 10 to the whole thing on the left is not necessarily equal to 10 to the this minus 10 to the that. What you can do is use the rules of logarithms. This is going to be the quotient rule, to rewrite this as log of 3x minus 2 over 2 equals log of x plus 4. So that's just the quotient rule. There was a subtraction on the outside, and I'm able to make it a division on the inside. And now I can do the same thing as I did before, except that log is base 10, so I'm going to raise 10 to the power of both sides, which cancels it out. And we get 3x minus 2 over 2 equals x plus 4, which I'll let you solve on your own time. You know how to solve a problem like this. I'll do as a quick review. I'll show all of our notes from before. So the domain, we have our log base b of x is the inverse of b to the x. The domain of log base b of x, the range, the x-intercepts, the vertical asymptotes. I should say, I'll fix this, should say common logarithm. The common logarithm is log x, which just means log base 10 of x. The natural logarithm is ln x, which means log base e of x. E is the natural number. We've got our properties of logarithms right here with our most important ones highlighted in gold and the sort of special cases scattered around them. We've got our laws of logarithms here, the product rule, quotient rule, and power rule. And finally, we have our lovely change of base formula, which lets you say that log base b of a is log a over log b if you want. Have a wonderful rest of your day. This is going to conclude our video on logarithms. I'm going to post as soon as I possibly can a video on our next lesson as well.